List all possible rational zeros for the function p of x equal to 3x cubed plus 4x squared minus x minus 2. Here we have the graph of the function p. Finding the zeros means that we will find the x-intercepts for this graph. They appear to be right around x equal to -1 and somewhere between 1/2 and 1. We will begin by assigning the lowercase p to be all of the possible factors of the constant term. These would be plus or minus 1 or plus or minus 2. Then we will assign the lowercase q to be all of the possible factors of the leading coefficient. These would be plus or minus 1 or plus or minus 3. All of the possible rational zeros of the function p will be in the form p over q. These possibilities would be plus or minus 1 over plus or minus 1, plus or minus 1 over plus or minus 3, plus or minus 2 over plus or minus 1, and plus or minus 2 over plus or minus 3. We can simplify this list by expressing the terms as plus or minus 1/3, plus or minus 2/3, plus or minus 1, and plus or minus 2. Now we will choose one of these terms and perform a synthetic division with the polynomial p as the dividend and our choice of possible rational zeros as the divisor. Let's choose one from the list and see what happens. We will begin by drawing a little half of a box. Then we will write our choice of 1 in the box. To the right of that, we will write the coefficients of the polynomial p. So we will write 3, 4, -1, and -2. Then we will leave a space and draw a line under the whole thing. Next, we will write the leading coefficient of 3 under the line. Now we multiply 1 by 3, which gives us 3, and write it under the next term, 4. Now we add the 4 and the 3 and write that sum directly below. Now multiply 1 and 7 together and write that product under the next term, -1. Again, add these values together and write the sum directly below. -1 plus 7 is 6. Again, multiply 1 by this value of 6 and write that product below the next term, -2. Now add these terms together for a result of 4. This value of 4 represents the remainder when we divide the polynomial p of x equal to 3x cubed plus 4x squared minus x minus 2 by the divisor x minus 1. The other values, 3, 7, and 6, represent the coefficients of the quotient polynomial. The result would be 3x squared plus 7x plus 6 plus the remainder 4 over the divisor x minus 1. The remainder theorem tells us that this value 4 would be the value of the function p when we substitute the value 1 for x. In other words, p of 1 would be equal to 4. We can verify this by substituting the value of 1 into the function p. So we would have 3 times 1 cubed plus 4 times 1 squared minus 1 minus 2 equal to 4. But we are looking for the values of x that would make the polynomial p equal to 0. So let's choose another value from the list and perform another synthetic division. Let's choose -1 this time. Again, write the coefficients from the polynomial p, beginning with 3, then 4, then -1, and then -2. Again, leave a space and draw a line below the whole thing. Pull down the 3, multiply -1 by 3, and write the product below the next term 4. When we add 4 and negative 3, we wind up with a sum of 1. Multiply negative 1 by 1 and write the product below the next term, negative 1. Again, write the sum below the line, which will be minus 2. Again, multiply and write the product below the next term, negative 2. Now, when we sum this last column, the result is 0. This means that we found a value for x, negative 1, which will make the polynomial p equal to 0. So this value, x equal to negative 1, is called a 0 or a root. We suspected that it would be when we were looking at the graph. We also found that 3x squared plus x minus 2 is a factor of the polynomial p. This means that we can factor the polynomial p into the factors x plus 1 times 3x squared plus x minus 2. This also means that we can now use the quadratic factor 3x squared plus x minus 2 to find the rest of the zeros for the polynomial p. So we will continue this process by choosing another possible root from the list. Let's try 2/3. So we will write 2/3 in the half of a box next to the last row from the previous division. We can do this since the last term is a 0. Now again, leave a space and draw a line. Bring down the 3, multiply 2/3 by 3 for a product of 2, and write it below the next term, 1. Add the 1 and the 2 for a sum of 3. Multiply 2/3 by 3 and write the product 2 below the next term, minus 2. Add the entries in this column, minus 2 plus 2, for a sum of 0. So we have found another root, x equal to 2/3. This also means that 3x plus 3 is a factor of the polynomial p. And setting this factor equal to 0, we find that x equals negative 1 is a root of the polynomial for the second time. So the zeros for the polynomial p are x equal to negative 1, x equal to 2/3, and x equal to negative 1 again. Whenever a root occurs more than once, we say that it has multiplicity. There is another path we could take for part of this problem. Once we have found enough roots so that we are left with a quadratic factor, we could set the factorization of the polynomial equal to 0 and then solve either by factoring, completing the square, or using the quadratic formula. Using the zero product rule, we can set each of these factors equal to 0. Again, we find that x equals minus 1 is one of the roots. In this example, we can factor the quadratic as 3x minus 2 times x plus 1. Now setting each of these factors equal to 0, we have 3x minus 2 equals 0, or x plus 1 equals 0. And again, we would find that x equal to 2/3 or x equal to negative 1 would be our remaining two factors. The significance of this process is that it has provided us with two important results. We have found the roots for this polynomial, and we have found the factorization for this polynomial.